AI mixture of experts, how senior engineers build scalable, cost-efficient models in production. Welcome back to Agentic AI World, the show where we break down what it actually takes to build, ship, and scale AI systems at a senior engineering level. I'm your host, and today we're diving into one of the most powerful architectural innovations in modern AI, mixture of experts, or MO. If you've heard about GPT-4, Gemini, or Mixtral, and wondered how they pack so much capability while staying practical to run, MO is a big part of the answer. Let's break it down like a senior engineer would in a system design interview. What is mixture of experts? At its core, mixture of experts is an architecture pattern where instead of having one big, dense neural network, you have multiple smaller specialized subnetworks, called experts, and a routing mechanism that decides which experts to activate for any given input. Think of it like a hospital. Instead of one generalist doctor handling every patient, you route each patient to the right specialist. A cardiologist for heart problems, a neurologist for brain issues, an orthopedist for bones. Each doctor is expert in their domain, and the hospital has a triage system, the router, that directs patients appropriately. In transformer-based MO models, this typically happens at the feed-forward layers. You might have 64 or even more expert networks, but for any single token, only 2 or 4 experts activate. The router, usually a small learned network, assigns weights to experts, and only the top K get compute. The result? A model with the parameter count of something massive, but the inference cost of something much smaller. The key numbers that matter in interviews. When you talk about MO in a system design interview, know these concepts cold. Number 1, total parameters versus active parameters. Mixtral 8x7b has about 46 billion total parameters, but only activates around 13 billion per forward pass. So you get the knowledge capacity of a 46B model at roughly the inference cost of a 13B model. That's the MO value proposition in one sentence. Number 2, top K routing. Most production MO systems use top 2 routing. Each token gets routed to its 2 best matching experts out of the pool. More experts means more specialization, but also more routing complexity and potential for load imbalance. Number 3, expert capacity. This is the maximum number of tokens any single expert can process per batch. If you overflow capacity, tokens get dropped or overflow to a backup. Setting this right is critical for production throughput. The router, the heart of MO. The router is what makes or breaks a MO system. It's typically a linear layer that takes the token representation and outputs logits over all experts. Softmax those logits, pick top K, and route accordingly. But here's the problem senior engineers know well: load imbalance. Without careful design, the model learns to always route to the same 2 or 3 popular experts while others starve. This kills the parallelism benefits and wastes capacity. The fix? Auxiliary load balancing loss. During training, you add an extra loss term that penalizes the model when routing distribution is uneven. This nudges the model to spread load across all experts. In Google's Switch Transformer paper, they used a simple capacity factor and auxiliary loss. In practice, tuning that auxiliary loss coefficient is an art. Too high and it overrides learning quality, too low and you still get imbalance. MO in production, the real challenges. Let me give you the 3 biggest challenges you'll face deploying MO in production. Challenge 1, memory versus compute trade-off. MO models have large total parameter counts. Even though you only activate a fraction per token, you still need to load all experts into memory or have a strategy to page them. For Mixtral 8x7b, you need around 90 gigabytes of GPU memory in FP16 just to fit the weights. That usually means multi-GPU serving even for inference. Challenge 2, expert parallelism. MO naturally maps to expert parallelism. You can put different experts on different GPUs. But this introduces all-to-all communication overhead. Each device processes its slice of a batch, routes tokens to the right expert GPUs, collects results, and continues. The communication cost needs to stay below the compute savings, or you've lost the benefit. In practice, frameworks like Megatron LM and DeepSpeed both have MOE-specific parallelism strategies. Know that you typically combine expert parallelism with tensor and pipeline parallelism for large deployments. Challenge 3, Dynamic routing latency variance. Unlike dense models where every input takes roughly the same compute path, MO routing means different inputs have different expert combinations. This creates latency variance that's harder to profile and SLA bound. Senior engineers instrument per expert activation rates, routing entropy, and token drop rates as key observability metrics. Common interview questions on MO. Let me give you 3 questions I've seen in senior AI systems interviews and how to answer them. Question: how would you scale a mixture of experts model across a multi-GPU cluster? Answer framework. Start with the parallelism hierarchy. Use data parallelism across nodes for batch throughput. Within a node, use expert parallelism to distribute expert weight shards across GPUs. Use tensor parallelism within individual large experts if they're big enough to warrant it. Add a load balancer at the routing layer to handle capacity overflow gracefully. Quantize experts in INT8 or INT4 to reduce memory pressure. Use paged attention for the attention layers. The key metric to optimize is tokens per second per dollar, not just raw latency. Question: what goes wrong with MO models in long-tail production traffic? Answer framework. Expert specialization can break down on out-of-distribution inputs. The router, trained on your training distribution, may route novel inputs